All right, we are recording now. We are live, and I'm going to go ahead and I guess before we start the screen share and start class today, I'll ask one more time. I asked before everyone was on, but does anyone have questions regarding logistics or any big concepts? And you can always send me an email and set up a time to meet one-on-one if you can't come to office hours. Today we had a couple people at office hours, and I got a heads up on, well, a head start on what we were doing tonight, but you can always join. I'll meet you anytime during the week, basically, that works for you. My schedule is quite flexible now. Everything I'm doing turns out is on Zoom. So thank you to those who actually have to leave your house and are doing a lot of stuff. I know that not everyone is as fortunate as me and gets to quarantine. I am one of those. Taylor, I'm going to mute you again. Taylor Arnold, that is. All right. So there's no questions right now. Feel free to stick around after class, and I'll be here for a little bit. I'm going to go ahead and share my screen, and we're going to get started on today's class. I'm going to go full screen, and I'm going to move my faces over here.
Also, light too, please. Maddie, light.
Who's that's unmuted? We got mute going. All right. I can't see everybody, but I wish I could see everyone on this other screen, but unfortunately just, oh, it looks like I can. Fantastic. Yes. Okay, now I can see everyone. All right. So we're gonna go ahead and I have location services turned off. I want you all to answer a series of questions. And today's theme is gonna be talking about conjugate acid bases and how that relates to salts. So to start off our conversation, I want us to think about some specific salts, and we're going to click in the anion for a number of different salts. These are not in the worksheet, but remember I did upload 2 worksheets. So once we get through this page, everything we do from that point forward is going to be on the worksheet. So go ahead and click in your responses for what is the anion when this salt dissolves in water. We got 6 responses. Make sure to click in your answer and hit the send button. All right, we'll do another 15 or so seconds. If you find yourself Googling the name and converting that into a formula, that's probably a pretty good sign that you might need to go freshen up on the different polyatomic ions. All right, a couple more seconds here and we'll close out. Closing out. Any last responses? Looks like we got 22 people in. All right, closing out. So we have a number of different responses. 81% say I minus. So really what we're talking about here is I want everyone to be very, very comfortable with going from a name to a formula. So the formula for this one, NH4, I, when it dissolves in water, we're going to do a single-headed arrow because of dissolving. If it's soluble, we're going to assume it goes to complete dissociation. And then we're going to end up with NH4 plus aqueous plus I minus aqueous. And then this is our cation, and this is our anion. And the way I remember that, cat has a plus in that T. That reminds me of a positive charge. That's how I keep cation and anion straight. All right, I'm going to put up the next 3 of these, and I'm going to throw us into breakout rooms for a minute. When I do that, I want you to go through each of the 3 and decide what the anion would be, thinking about that dissolving process, that first step of everything else that we're going to kind of work on. So here's the other 3. I'm going to go ahead and send us to breakout rooms, and It's not popping up. There we go. So you can discuss, check with others. We're going to go into, how many rooms do we want today? Let's do 4 rooms. Automatically create makers. All right, go for it. Do you have the option to move now?
Is it supposed to send us?
It is. I realize right now, there we go. Alexandria, can you join that breakout room? Does it show up as an option for you? Stacy, how'd you feel on the homework?
From this week?
Yeah, for like the primer for today.
I guess I thought it was okay.
Pretty straightforward on your account.
Yeah.
Sweet. So once we get everyone back, Stacy, do you mind giving us a formula in one of these? And then can I get volunteers for the other two? I see a little physical hand raise like this. I'll try to pick you out. Anyone wants to volunteer to give one of the other 2 formulas and anions? No hand raises. Tina, we'll have you do the 3rd one. Stacy, you'll do the 2nd one. And then I'm going to take Sam's drinking the bottle as a volunteer to do number 4. All right, so Sam, you're going to tell us what the answer number 4 is when we get there. So Stacy, what did you get for number 2? Or you and your group get?
For the second one, I said the anion would be NO3.
Almost. What do we miss?
Um,
Anyone
Negative
help?
charge.
There we go. Tracy.
NO3 negative.
Yep. So that
Maybe not.
negative charge is really important. That was what makes it an anion. That's a negative charge component. And so what
Oh,
was
I
the
thought it
salt
was-
potassium nitrate? Sorry, Stacy, you broke up there. Can you say that again?
oh, I didn't include the negative sign because I thought it was implied since it was an anion.
Yeah,
I'll
so
remember to write it
sometimes there's one negative, sometimes there's two, sometimes there's three. So if we said phosphate would be PO for. And so if we don't include the 3-, we can't just say it's an anion with PO3. It's really important to say how many negative charges it has. So it's a good point. Thanks for bringing that up. All right. And what, Stacy, what was the formula for potassium nitrate? We should have that up there as well.
For potassium nitrate, it was KNO3.
Great. And so when that dissolves, we get these two ions, of which the anion is this guy. All right, Tina, you said we're going to go for number 3. So what's the formula? And then what's the anion once that dissolves?
Yes, for potassium cyanide, I got KCN. And then we said the anion would be just CN minus 1.
Great. And then potassium ion would form as well, but the anion is CN minus. Great.
Right.
And then Sam, dimethyl ammonium chloride. I kind of give you the terrible one. What's the formula?
I think the formula was, I couldn't find it. I wasn't sure what it was, but I knew that the anion was chloride with a negative charge of 1.
Great. And then this is the compound that we worked with last class. So dimethyl, di means 2, methyl means CH3, and then ammonium means a nitrogen with 4 things attached to it and a positive charge. So this is dimethyl ammonium chloride. So when that dissolves, we get chloride and dimethyl ammonium that's separated out. So this might seem like a really, really simple exercise. And the point of doing this for me was to get you thinking about when things go into water, we want to start looking for what are going to be the cations and anions. And then each one of those are going to have different properties in water. Some are going to act as acids, some are going to act as bases, and a lot are going to act as neither. So that's kind of where we're going today. So let's see if I can stop this poll. The poll wasn't really used in that one necessarily, but I just wanted to send out the image of the screen that we've been working on. So by the end of today's class, I want you to be able to determine the pH of a solution of a salt. So looking not just at what are the anions and the cations, but how will they influence the pH. Predict what happens when you add a product or reactant to a reaction equilibrium. So we're going to talk about Le Chatelier's principle. There are videos assigned for Wednesday's class. I think it's a 10 or 15-minute video for the for the primer. It's basically you click on it. It's not really about credit. It's about watching it to kind of give you an idea. There's a crash course chemistry that's fantastic about it. So I thought instead of me trying to replicate that, I'd have you watch it, and that'll be the basis for our discussion on Wednesday. So part of this is predicting the pH of a solution that has a weak acid or a base. I don't know why there's no E in that. And we'll talk about kind of what common ion means. And then finally, determine the pH of a buffer. This is going to get us really into Wednesday's class. A lot of what we're doing is building up to support what you've done in lab with titrations of adding a strong acid or base to a weak acid or base and looking at pKa and how that all relates. So hopefully by the end of this week, that will all kind of merge together and you'll see kind of how it fits together. So let's take a look at this dimethyl ammonium and dimethylamine that we talked about a little bit last class. I want you to think about if we add one of these to water, which one is going to make it acidic? So go ahead and look over these 4 options. This was also the end of your worksheet last class. We didn't get to answer this question.
Are we supposed to be seeing your screen right now?
Did it not share screen? I sent it as a
don't see
clicker
it.
as well, but I think when we got out of breakout rooms, I think you're right. I think it disappears. Better?
Yeah.
Thank you, Aislinn. Couple more seconds. All right. So let's check out our responses. Looks like we're mixed. So about half the class answered B, but then a whole bunch of other people answered some other ones. So why is our answer for this one B? Can I hear from, let's see, a volunteer? And I think if you hit the little button at the bottom of your screen, is there an option to raise hand? Or maybe you can just unmute and share your thoughts. Oh, Stacy's raising her hand. I can see that. That's pretty cool. Go ahead, Stacy.
Would it be B because B would donate a proton to form the hydronium ion?
So I think your audio is breaking up a tiny bit, but I think you said that if we combine each one of these with water, then you would end up with this one donating a proton.
Yeah.
The one above it, if you combined it with water, that one is a base that we talked about last time. Because it has a nitrogen with a lone pair of electrons, that one is going to accept a proton from water and act as a base. Water is not, well, I guess it can act as an acid and a base, but it's, if you add water to water, it's not going to make the solution a lot more acidic or basic. And then hydroxide, if we add that to water, obviously that's going to be a strong base. It's going to act as a base and it's going to pull a proton off of water. So it's going to make the pH higher. So what I want to start and think about is whenever we see a compound, we want to think about what would the conjugate acid or base of that be? And is it likely then that this is going to act as an acid or is it going to act as a base? Once again, if you see nitrogen with 3 things attached to it, it means that it's going to act as a base because it has a lone pair of electrons. If you see a nitrogen with 4 things attached to it, that's going to, if one of those 4 things is a hydrogen, it's going to act as an acid and donate a proton. So what I want us thinking about is, or the way we can look at that as well, is that we have our equation we saw at the end of the last class. If you take your dimethylamine, put it in water, we have our conjugate acid base pair. I totally made that backwards, didn't I? That was useless. Base and acid pair, just to make things
Dr.
super clear, right?
Bailey, did you say if it's got 4 things attached to it, it's going to act as a base?
So a nitrogen with a lone pair acts as a base. That means it can only have 3 things attached to it. If we have a nitrogen with a hydrogen and 3 things attached, it's going to have a positive charge. And that's going to act as an acid because this proton can be donated to get it back to a state where it has a lone pair and 3 bonded atoms to it. So remember, the definition of an acid is something that can donate an H+ ion. And that definition of a base is something that can accept. So whenever we see these 2 things in relation to each other, we're always going to know it's a conjugate acid base pair. So while we can describe that last scenario as something that is, and we can add this to make an acid in water. The thing is, you can't really, we got to think about stability of what actually exists in nature. Something with a positive charge isn't something you can go get on a shelf. We can't find hydroxide on a shelf. OH minus doesn't exist by itself. H plus doesn't exist by itself. All of these things only exist in the form of neutral salts. So I can go on a shelf and I can get sodium hydroxide. When I put it in water, it generates OH minus because the Na plus and OH minus separate. Same thing with H plus. I can put HCl in water, and when that dissolves, I end up getting H plus and Cl minus, or H3O plus. So in order to get this compound that we just said was the conjugate acid of our weak base, we can't just put that into water. So that's why one of our problems earlier, we talked about dimethyl ammonium chloride. So what I want us thinking about is we make a solution with 0.1 molar of dimethyl ammonium chloride. I want you to figure out what the pH of that solution is. I've given you the Kb of the conjugate base. So I want you to go ahead and I'm going to put you back in groups, and I want you thinking about how we can determine the pH of this solution. I'm going to send this out to your phones through the clicker, and then I'm going to send you to breakout rooms. All right, let me see if I can get this to send. Come on, buddy. There we go. Breakout rooms. We have 7 people in one group though. I think I'm going to send one of the Sydneys to breakout room 5. Go. Did the breakout rooms get started? They didn't get started, did they? There we go. Sam, are you not assigned to a group or room? Let's send you to that room. Alexandra, are you going to join your group? Do you see that thing pop up on your phone or your screen?
Are all your other classes online as well? Is that like nice for some classes? No.
Yeah, I'm not really liking it, especially with physics 2.
Oh God, I can only imagine what that's like.
Oh, I failed physics 1. Terrible.
Physics 1 seemed pretty straight to me, but physics 2 wasn't going too bad until this happened, and I can't ever talk to the guy, but he posted some stuff, and it's like basically talking about like time travel.
And man, quantum is where it's at. That stuff's incredible. Relativity, super cool.
That's what this is. It's special relativity.
I was never smart enough to do well in physics, though. I feel like that is just a whole nother level. Quantum entanglement, all that stuff is just like
Well,
All right,
this is the
we have
end of that
18
road
responses
for me.
clicked in. There. 18 responses clicked in. And if anyone else has a number to send for your answer, can I get a new volunteer to talk through high level what you decided to do? And maybe I can kind of scribble it down as we go. Can I see a hand raised for a new volunteer? Carter, go for it. I think you're muted, buddy.
I can get us started at least. So you gave us the KB. And so when we have the KB, we can find the KA. So you divide 1.00 times 10 to the negative 14 by the KB.
What'd you find for that number?
1.69 times 10 to the negative 11th.
Okay, that sounds reasonable. And then what'd you do once we had the KA? Why do we need the KA here?
Because we're not trying to find the other side of the equation. I don't know what the word is for, but not that side of the equation. So we need the KA.
Okay, so I'm gonna just clarify that a little bit. And it really just depends on, are we putting the acid in solution or are we putting the base in solution? And in this case, we decided that we're putting the acid into solution. So this ice table is only described by Ka. If we describe it by Kb, then we start with products and we have to work our way backwards, and it's not gonna work out well. So always do it based on what you have on the left side of the equation. All right, and then now that we have Ka, what do we do?
We set up our rice table.
Okay. And when we do that, we're gonna get, I'm gonna skip to the bottom here, x 0.100 minus x, and then Ka equals x squared over 0.100 minus x equals 1.69 times 10 to the negative 11th. All right, then what do we do from that point?
After you solve it out, you get 1.36 times 10 to the negative 6.
What is that?
That is the K.
That's what?
What'd you ask?
What is 1.36 times 10 to the negative 6th? What did you solve? When you say you solve for, what is that?
Oh, X.
Okay, and after having done this for 6 years, the most common question I get is, then what do I do? Solving for X, we have a process, right? We do the ice table, we get an X value, yes. And then do we use 1 times 10 to the negative 14th to do something with it? Do we take the negative log? Do we take the negative log and then subtract that from 14? So this is really the most crucial part of solving for the pH of a weak acid or weak base. Is the question, what is X? What did we just solve for? And why does it matter? Carter, you want to continue on that, or you want to pass the baton?
I think I'll pass it on this time.
All right, Lauren, can you help us out here? What is the X that we solve for, and why do we care about that X?
Well, we know that X is going to be the concentration of H3O plus, and that's what we want since we're looking for pH.
Great. So X is a number of different things, but the one that we care about is X is the equilibrium concentration of H3O plus. And the question, what is the pH? Basically there. So this, it's really good to add the last step. This is the equilibrium concentration of H3O plus. So now how do we go from the concentration of H3O plus to the pH? Aislinn, what's our last step there?
Sorry, what'd you say?
What's our last step now that we have the concentration at equilibrium of our H3O plus?
Do the negative log.
Of our concentration of H3O plus at equilibrium. Great. And what did you find for your numeric value?
5.89.
So I heard a couple people asking how many sig figs should we have here? And normally what we're going to do is we're not going to limit our sig figs to the known value that you can go look up in a table somewhere more accurate than that. So I would actually limit my sig figs to the concentration. So we had 3 sig figs starting. So I would report 3 numbers past the decimal for this answer here. So what is the, does anyone have that 3 past the decimal? Maybe I can go look at the clickers.
5.885.
885. Okay, so that is the pH. Do we need to check anything? Do we need to make sure the number's reasonable? Do we need to make sure we have any assumptions checked? I'm gonna ask Sydney in the yellow shirt. Sydney, what do we need to check?
Do we need to make sure that it's something about 5%, less than 5% or something?
Yes, what is that? What do we do to check that?
I don't remember.
Kevin, you help out? How do we check our assumption?
I don't know either.
All right, can I get someone that's confident in this?
You divide the concentration of the hydrogen on the right side to the concentration of the, or you divide it by the concentration of the acid to begin with.
Okay, so we're basically saying, was this change in our initial concentration substantial or not? If it's less than 5% of this value, we're good. But if it's a significant amount, then we have to do the quadratic. So we're going to do x divided by our initial value of concentration times 100 to make it a percent. And if we do that, we end up finding that that is a very, very, very small percentage. My batteries are low. So 1.36 times 10 to the negative 6 divided by 0.1 times 100. So I end up getting that it is 0.00136% ionization. That is a really, really small amount. So we can say that the assumption and there's one other thing. We're looking at a numeric answer. And to be honest, we should have done this before we started. What side of a pH of 7 do we expect our answer to be on? Should it be higher than 7, lower than 7, or should it be at 7? Amber, which one would you say and why?
Lower.
Why?
Because if it's lower than 7, it is acidic.
Okay, and we're putting what we said was an acid into water. That's why we're describing it with Ka. So what a lot of people will do is, I heard some side conversations in the group chats, is that this idea of, well, if we're not completely comfortable with what X is, and we do try to figure out how it works with the concentration, is the concentration OH minus or H plus, then a lot of people will flip it and end up giving you the POH instead of the pH, or not knowing which one they're doing. So all we can approximate first, say it should be above 7 or below 7. Are you guys hearing me okay? Am I getting pretty digi? Thumbs up for not digi, thumbs down for digi, a little bit digi. Mixing, dang it. Okay, are you following or do you have questions? Let's pause there for questions.
Did you say
Going
anything?
right?
I'm sorry.
Go ahead, Sydney.
Say anything after you said the assumption is valid, because it cut out on mine.
The assumption is valid, and then I had, we discussed whether it should be a pH above or below 7. And so, did you hear Amber's?
Yes, I did. Yeah.
Yeah. Yep.
Thank you.
That's it.
I have one question. It's going back to the one we just did. Could you work out how you actually find the X value? Like go through the steps of finding it whenever you have the Ka and then you have X squared over 0.1 minus X. Could you?
You mean how to, so let's do when I was here. So you're saying that to go from this equation to actually finding the X value?
Yeah.
Okay. So we made the assumption that this minus X was really small. So we have this is equal to our Ka value. So then we multiply Ka times the initial concentration of 0.100. Once we have that number, we take the square root.
I got you. So when it's a weak acid, you just kind of neglect
that work?
Sounds good.
When it's a weak acid or a weak base, we make the assumption that the change is small. And if we do that, then we have to check our assumption afterwards. All right, so what we're gonna do now is a couple of questions where we're gonna go and talk about a new solution. So this new solution is our dimethylamine in solution by itself. And this is the one we ended last class on. And what I want us thinking about is if the diethylamine is in solution, we have a 1.50 molar solution of it. The pH is going to be basic because it's a weak base in water. Now I want us thinking about, we're going to make a mixture of a conjugate acid-base pair. And this is something we're going to start talking about as a buffer here in the next couple of days. So the first question is, if we have this of a solution, and I just want you thinking logically, don't think too hard about this. What's going to happen to the pH when we add dimethyl ammonium chloride to the solution of just diethylamine? Go ahead and click in your answer to this first clicker question here. And I believe this is on the worksheet for today. All right, we're at 17 responses. And Michael, how do you feel about sharing your thought process for answering this question? Am I frozen? Dang it. Can you guys hear me? Looks like I just froze out for a little bit. This is terrible. Okay. Michael, can you hear me? Michael? Maybe not so much. Kat, can I hear from you? How
Can you
would you
say
answer
that
this
one more
question?
time? Oh, sorry. Sorry, my dogs are really loud. Can you get them out? Okay. I put that the pH would go down only because I view, I believe dimethyl ammonium chloride is an acid, and adding acid to something that a base would make it go down. That was just my thought on it. I didn't think too much about it.
Great, that's exactly what I wanted. So a lot of people get confused and they'd be like, what about the mixture? What's happening to the mixture? But if you just think about it as, even if it was neutral water, you're adding an acid, so pH is going to go down. Now we're talking about a basic solution with a higher pH. The pH is still going to go down. Okay, so let's think about why that happens. So two more questions. The first one is KB going to change when you add and make a mixture? Go ahead and click in your responses. Couple more seconds. All right. Samantha, what did you answer and why?
Okay. It takes forever to unmute. I put KB would not change because isn't K is a constant, so doesn't that not change regardless of what's added into the solution?
Absolutely true. So KB is a constant. If we have a different temperature, KB will change. But remember, KB is defined by the concentration at equilibrium. So if we have a different amount of things in there, KB is not going to change. But what about Q? Go ahead and click on your responses for the last one. All right, we're going to go ahead and take a look at the responses for this one. Fantastic. So what we're saying is that when you add in dimethyl ammonium chloride, the most stable mixture would still be the same. But what we've done is we've added more of one of these two components, or one of these three components, which means the Q value is now going to be thrown off. So then to reestablish equilibrium, after we've added some ammonium chloride and that number on the Q value is higher, what has to happen in order to reach equilibrium? Are we going to convert reactants to products, or are we going to convert products to reactants to get Q to come back down to K? Couple more seconds. All right, Gabby, can I get your thoughts on this one? How did you answer this?
I'm not exactly sure. I just kind of made an assumption that Q would maybe be more than KB. And
okay, that's true. And so what would happen for Q to get back, those concentrations to change to get back to where Q does equal K at equilibrium?
the products would have to convert to reactants to like make it go back to equilibrium.
Fantastic. And we had a bit of a mix here. A slight majority of class agreed with you, and I agree with you. So basically what we're saying is that if we make the top value, we had it in equilibrium, and then we added, after we're at equilibrium, we added some of the thing on the top, made Q bigger than K. In order for that number to get back to a ratio that is at equilibrium, where Q does equal KB, we have to take both of these and make some of the reactants. So that process, that leveling out, is called the Chatelier's principle. It's basically this idea that if we have a system at equilibrium and then we mess with it somehow, we either add more products or add more reactants, or take away products or take away reactants, what we're really doing is we're changing Q. So Q is no longer equal to the equilibrium constant. And then given a little bit of time, or a lot of time, depends on the situation, in the end, all of those are going to shift so that our Q is back to being at K. So an example of that is the Haber process. So this is a reaction that we did talk about a little while ago, where it's how fertilizer is made, or part of fertilizer. So NH3 is ammonia, that's used in a lot of fertilizers, and it's made through this process of fixing nitrogen, pulling nitrogen out of the air, which is 80% of all air molecules, and combining with hydrogen gas, and we make ammonia, and it needs a catalyst to do this. So the statement that's at the bottom of your worksheet for today is this statement here. if an external stress is applied to a system that is already at equilibrium, the system adjusts in such a way that the stress is partially offset, and the system reaches a new equilibrium position, but it has the same equilibrium constant. So basically we're saying if you add or take away something, Q no longer equals K. We're not at equilibrium anymore. But that Q then has to do something in order to get back to K. So if we had a system that was equilibrium and we added a product to it, in order for that system to get to equilibrium, those products would have to be converted back to reactants because our Q got too big. That's kind of what we just talked about. And Q would have to decrease in order to get Q to equal K again. So here's an example where we have an initial concentration of 3 different things at equilibrium. So this is the Haber process again. You'll notice that it's at equilibrium. Remember, we use these square brackets to say concentration at equilibrium, and we use parentheses to say concentration in molarity not at equilibrium, or we don't know if it's at equilibrium. So the first thing I want you to do is ask you to click in the numeric value of your equilibrium constant. So you have, I believe on the top of your second page on the worksheet, you have these values as well, but I want you to determine Kc for this reaction. Let's do about 20 more seconds. All right. I'm gonna go ahead and take a look at the responses from the clicker poll. And it looks like we have a few different numbers kind of all over the place. The one that got the most traction was 4.07 or 4.1. So let me ask, did everybody remember what the expression for Kc is? Concentration of products at equilibrium raised to the stoichiometric coefficient over concentration of reactants raised to their stoichiometric coefficient. So when I did that, I got 4.07, but looking at our sig figs, we only have 2, so 4.1 would be appropriate sig figs for that. Okay, so that is the mixture when it's at equilibrium. So what we're gonna do next is we're gonna talk about what happens if we add a stress to the system. So in this case, we're gonna take this exact mixture and we're gonna add some hydrogen gas into it. We're gonna go inject some into it. The new concentrations at that point are here. So you'll notice that at the exact second when we added hydrogen gas, we have not yet changed the concentration of these two. You notice those are the same. What we did was we increased the concentration of hydrogen gas. Follow me? So then the question is, what's going to happen to the concentration of hydrogen after that Q is now different? So we're looking at the concentration right after it was injected. Is it going to go up again? Is it going to go down? What's going to happen? Not going to change. So we'll do about 15 seconds for this clicker question. All right, closing out. So do we have Taylor? How did you answer this question and why?
Me, Taylor?
Yes.
Okay. So my thought process was when you add in more hydrogen, that will mean that there will be more reactants than products. So that means that in order to reach equilibrium again, it needs to shift to the
right?
To the right, yes.
Okay.
So that means it'll go.
Yeah, if we simplify, so you're definitely on the right track. So if we now have more reactants than products compared to equilibrium. That's a really important point, because if it's just compared to each other, we don't know where that is compared to equilibrium. So it's always equilibrium is this, and now we have more reactants than that mixture would be at equilibrium. So the reaction will have to shift to the right, which means we use up reactants and we form products to get back to equilibrium. And we were 50-50 on that. So the concentration after that initial injection is going to go down. The reaction shifts to the right. What's going to happen to the concentration of nitrogen at this point? Go ahead and click in your answers. So we determined that the concentration of H2, once we had that initial injection, is going to be consumed. It's going to go down because the reaction shifts to the right. So what's going to happen to the concentration of N2? A couple more seconds. I want Aislinn to describe what she chose and why. Aislinn?
I said that the concentration of N2 would not change.
Okay, let's see if the class agrees with you. We're all over the place. So if we said the concentration of H2 is going to go down, how does the concentration of H2 go down? Anybody want to take a stab at this?
It's going to have to react with nitrogen.
And if it reacts with nitrogen, then both of them have to go down. You can't get rid of hydrogen without using up the nitrogen gas in order to react. So conservation of mass is really important. So last question. We're using up hydrogen, we're using up nitrogen because Q wasn't equal to K. So what's going to happen to the concentration of NH3 as this reaction proceeds from that initial injection of H2? Couple more seconds. All right, I'm going to close out, and can we hear from Lauren what's going to happen to concentration of NH3 and why?
I said it would go up. Since we're using up the reactants, we'll get more product.
Does the class agree with you? 100% so. Absolutely. So here's what that looks graphically. So this blue spike is where we added hydrogen gas. At that initial time, we had equilibrium here. Now our Q is way off because our hydrogen value in relation to NH3 and N2 is not in the right ratio to be Q is equal to K. So in order to get there, our Q value was lower than K, so we had to use up our reactants. Both of our reactant concentrations go down, and then in doing that, they make our NH3. When we get to the new steady state of those concentrations, that is equilibrium, and our Q is going to equal K again. So let's take a look at another generic reaction. If we have a reaction where we have two reactants combining to form two products, I want you to click in what change we're going to see if we increase the concentration of one of our products So we were at equilibrium and then we added C. So which way is the reaction going to proceed to get back to equilibrium? Is it going to proceed to the left, to the right, or is there going to be no change? So go ahead and click in your responses. And I think you have a little table in your worksheet to fill in for that. Couple more seconds. Does anyone want to try to describe why they answer the way they did with in terms of Q and K? Let's take a look. We have a 4-to-1 response that the reaction is going to proceed, what does that one say? To the left. So can anyone explain why they said this answer in terms of Q and K?
After you put some C in there, then Q will be a bigger number than K. And the reaction is going to have to push towards the reactants to re-equilibrate.
Fantastic. What happens if we decrease our concentration of D for the reaction that was already at equilibrium? Which way is the reaction going to go to reach equilibrium? Couple more seconds. So if we're removing some of the product, there's a little bit more of a mixture here. But if we remove our product, our Q is going to get smaller than K, meaning that in order for the reaction to get back to equilibrium, we're going to have to push this reaction to the right because this is now less than it was at equilibrium. The top of our Q and K is smaller. That means the reaction has to proceed to the right in order to fill that Q to get back up to K. 2 more. If we increase the concentration of B in a reaction that is at equilibrium, we basically added one of the reactants. What has to happen for the reaction to reach equilibrium? A couple more seconds. Go ahead and close this up. So if we're increasing the concentration of one of the reactants, the reaction is going to proceed to the right because our Q now became less than K. The reaction has to push right in order for that reaction to get back to equilibrium. Last one. If we increase the concentration of A, what happens? Michael, sorry, I see your response in the chat window now. My apologies. All right, and we'll go ahead and close out. So if we take away some of one of the reactants, we end up getting the reaction needing to shift to the left in order to compensate for that takeaway. That Q became greater than K, and we have to shift it back. All right. We watched the video before Wednesday's class. Hopefully that'll help even more with kind of getting this all together. So the last part of class, I'm going to send you into breakout rooms for a couple of minutes. In this one, I want you to try to make your best guess, thinking about the very first thing we did in class, what the salt separates into. And then once we've talked about that for a minute, we're going to come back together. So I'm going to send everyone into breakout rooms now. right, we got a lot of people back. Who's the dog face? There's 2 dog pictures, and I have no idea who they are.
Patrick is one of them.
Ah.
The one with the tongue out.
Yep. I can't call on the person if I don't know who their picture is. So thanks, Patrick. Now I can call on you.
Oh, yeah, that's me.
I'm sure that's exactly what you wanted. Patrick, do you want to take a stab at explaining this once everyone's back? At least how you might have started to approach it?
Well, I'm not really sure how to do it, but our group came up with A as the answer.
Okay. And I'm going to guess we had a 75-25. Okay, so we had a split, 75-25 split. So how do we do this? So let's go back to the very, very beginning that we talked about. So can I hear from Sydney Chastain? How do we going about a problem like this? What did your group discuss?
So we decided that the potassium cyanide splits into K plus and CN minus. And because K plus is, I believe we said neutral, and the CN minus is a basic, that our pH is going to have to be above 7.
Fantastic. So the major steps are, first you think about, is it a salt? Whenever you get any compound and you say, is it going to be acidic, basic, or neutral? Always think, are we looking at an acid, a base, or maybe a mixture of both? So that's separating out into the 2. We can look at 1, and as Sydney said, CN minus, we might not recognize it as a base right away, but hopefully if we see something with a negative charge, one of the first things that comes to our mind is that it might be a base. So we say, let's put it in water, see if it accepts a proton from water. If it makes sense, we can say that that's Ka. And we've probably seen HCN as a weak acid in some of our other practice problems. So we can say this is a conjugate acid base pair. CN minus is the base. Therefore, that alone is going to make a basic solution with a pH higher than 7. The other question is, well, what about your second component, K plus? Does it make any sense that it takes a proton from water? If it does, it would give you this KH2 plus. That makes no sense at all. So that's not going to work. It doesn't even have a hydrogen to give up, so it can't act as an acid. So we always look at what are the components that split out, and do they act as an acid or a base? Could you find the pH, the exact pH of the solution? Give me a thumbs up. You think you can find the pH? Maybe not so much. Let me see some thumbs up, thumbs down. Could you actually calculate the exact pH of this solution? Maybe, maybe. Okay, so I see some mixed thumbs there. Can I have someone who gave a thumbs up, maybe just give a really brief description of how we would find the pH of the solution, the process? Tina, can I ask you to share?
Sure. So since we have, sorry, we would have to set up the rice table first.
Okay. And in this case, I can't remember if I said it was K or KB. We have KB expression, so this is our reaction. We have our initial change equilibrium. In the end, what is our X value that we're solving for in this table? Tina?
Sorry, could you repeat that again? You were breaking up a little.
When we solve for X from this ice table, what is that X value that we're solving for? Why does that help us answer this question?
Are we going to solve for the concentration of well, X? Yeah, we're going to solve for the concentration of OH.
So if X is going to be the concentration of OH minus at equilibrium.
At equilibrium.
So if we take the negative log of that, is that our pH?
That would be POH.
Great. So we can find our POH, and from that we can do 14 equals our pH. So I highly advise you to practice doing that for this head and show the next one and see if we can really quickly take a guess at whether ammonium iodide is going to be acidic, basic, or neutral. So go ahead and click in your response. And then look at the one just past that as well. Couple more seconds to click in your response to this question. Questions, answers are rolling in. We have a 2-to-1 split. More people are saying that it's going to be acidic than are basic. So let's think about the steps. Ammonium iodide splits into 2 ions. Those 2 ions, we think about what is each one going to do in water. Our ammonium is going to act as an acid and generate ammonia, 4 bonds to nitrogen, 3 with a lone pair. Iodide, the question is, does iodide act as a base? Can we write I- plus H2O gives HI plus OH minus? Is that a reasonable statement? Does anyone want to argue that that is not reasonable? Anybody? So what's wrong about the statement here?
It's wrong because HI is a strong acid and it would completely dissociate. There is no forward and reverse reaction.
Fantastic, well said, Kat. So if we're saying, does this thing act as an acid or base? And we see that in order for it to pull a proton off of water, it generates a strong acid. That's never going to happen. So this is why I really need you to memorize your 6 strong acids. If you ever see a strong acid as your product in an equilibrium, that will never happen. So this reaction is only going to be acidic. It's only going to have a pH of less than 7. So once again, feel free to go through and calculate out the pH of that solution. The last one I had, I guess I had 2 more. We had sodium phosphate. And once again, separating out into its ions, we can write phosphate acting as a base. And our sodium can't donate or accept a proton. And then the last one is potassium nitrate. Do we want to do this one as a clicker, or you guys want to go? We done? I'll go ahead and leave this open. If you have to run, go for it. If you want to stick around for another 1 minute, we can answer this question. And I'll keep it recorded so you can watch the end of the recording if you want when I post it later tonight. 7 responses. So I'll put the first step up there because I think we would probably be on the same page. Potassium nitrate dissolves in water to generate potassium ions and nitrate ions. The question then becomes, what is the pH of this solution? So we have a total mixture of answers. Some people say it's going to be greater. So if we write out, more people said this than any other answer. So let's see what they might have said. They said NaO3 minus plus water generates HNO3 plus OH minus. Is that okay? Is that a good description of a base? Aislin's shaking her head. At least I'm making it out that she's shaking her head.
I wasn't shaking my head at you. Sorry.
Do you think that this is a reasonable reaction to write out?
No, because isn't that another strong acid?
So this is a neutral solution. So it's really important that you memorize your strong acids. Otherwise, you're not going to recognize them in the products and you're not going to know what you're doing. Okay, that is it for class tonight. We'll start up on buffers, basically applying this to understanding buffers in class on Wednesday. So please make sure you watch that video and make sure you do your primer. If you need to meet with me in the meantime, if you have questions about what we did tonight, please just send me an email and I'll make time to meet with you. Thanks. And I'll stick around for a few if you have any questions to ask.